Hello everyone. In this lecture I shall discuss the Cauchy integral theorem and what is also known as the Cauchy-Goursat's theorem or Cauchy's theorem. So you mark this statement carefully. If fz is analytic in a simply connected domain, then for every simple closed path, you mark these three words. Fz is analytic, the entire domain is simply connected, and then every simple closed path C in D, the integral C fz dz is equal to 0, right? Fz dz is equal to 0 means, suppose we have a simply connected domain. This is my domain D. Now in this domain we have a closed path and fz is analytic here, and within this domain we have a closed path. C here. This is a closed path C here, right? Then for every simple closed path C, integral C fz dz is 0. Then over this path, this integral is 0. Means if fz is analytic in this domain, right? So now this theorem, the restatement can be written like this. If a complex valued function fz is analytic on and within, right, means only this path C is given. To make this theorem more simple, we have a simple closed path C. Right, this is a simple closed path C. Now if the function is analytic, inside as well as on the boundary, right, everywhere, then the integral over this curve C, and the path is simple and closed, means there should not be any intersection of this path, intersection of this curve, right? Then the integral of fz over this path is 0. This is another restatement of this. Okay. However, the original statement is like this: fz is analytic in a simple connected domain. In this domain it is analytic, and this domain contains a closed path C. Obviously over this closed path it is analytic. Then integral C fz dz is 0. Sometimes this simply connected is necessary. I will show you some example. Actually, the original theorem of this Cauchy, it is also known as the Cauchy's theorem. It was something like, if f dash z is continuous, right? F dash z is continuous. So means f dash is continuous means fx is differentiable, which implies here Cauchy analytic. Then Cauchy Riemann holds. So the analyticity gives a better proof to this, and it was being modified by the Goursat. So combinedly this theorem is named as the Cauchy-Goursat's theorem. So this theorem, either it is called this Cauchy's theorem, or this Cauchy's integral theorem, or the Cauchy-Goursat's theorem. However, the original Cauchy's theorem is different, means f dash z is continuous, right? So now if I see some example, suppose you are given a, if you think of some example, suppose the path C is, suppose you say z mod is equal to 1, the circle here, right? Z mod is equal to 1, the inside of the interior of the circle. Then what will happen here? And you ask, and it is asked, integral C e to the power z dz. What will be the integral? Integral C cos z dz. You see, the function e to the power z, this function e to the power z, the function cos z, these are analytic everywhere, is not it? These are analytic everywhere. Therefore, this integral value must be 0. And the path is a circle I am taking, or rather if I take any closed path, then also this will work. Now once the function is analytic and the path is closed, right, then this integral is 0, right? So the restatement also instead of this domain we are taking this path, but this simple connected domain is also necessary. Coming to one more example, suppose you are given that C is here z mod is equal to 1. This path is enclosed by this circle, unit circle, and you are asked to evaluate integral C here dz by z square plus 4, z square plus 4. So this z square plus 4, this is not analytic, right? When the denominator 0, not analytic at z is equal to plus and minus 2i. Z square plus 4 0, so z is plus minus 2i. But what is the path here? The path here is a unit circle, right? Here center 0 and radius 1, center 0 and radius 1. So where is your I and where is your 2i? Here I is, right, 2i is here, this is I point, and your 2i is something here, and your minus 2i is something here, right? That means it is analytic everywhere, inside and on this path. That's why this integral is 0. So we write this function fz is 1 by z square plus this 1 by z square plus 4 is my fz, right? This is analytic everywhere except at plus minus 2i, which is outside C, right? This is outside C. So inside C and on C, this is analytic throughout. So this integral is 0, right? So this Cauchy integral theorem is very easy once we find the analyticity of this function, right? Once the analyticity is ensured within the curve as well as on the boundary of the curve, then the integral is 0 here, okay? So before the details of the discussion, let me to introduce myself. Myself, Professor S.K. Paikray, Susanta Kumar Paikray, currently working as a Professor of Mathematics at Surendra University of Technology, Burla, Sambalpur, Odisha, India. So without much delay, let me to discuss the further details of this theorem. And I can say here, the converse of this theorem is not necessarily true. The converse is not necessarily true. That means if the integral is 0, right? If this integral is 0, this doesn't imply that fz is analytic, right? If the integral is 0, that doesn't imply the function is analytic. So that's why this analyticity condition is sufficient only. It is not necessary, because the integral may 0 even if the function is not analytic. That's why this is called the sufficient. This theorem is sufficient condition, not necessary, okay? Now this necessary conditions is asserted by another theorem is known as the Morira's theorem. I will discuss. So now the sufficient condition is due to the Morira's theorem like this. The necessary condition, if fz is continuous, right? If fz is continuous, the domain is simply connected same and integral 0, then the function must be analytic. So the continuity of the function is necessary here. The continuity of the function is necessary to make the converse of the theorem is true, okay? So we will see one example here. You consider one example. You see that this integral is 0, right? But this integral is 0 here. This integral I is equal to 0 here. But this function is not analytic. Not analytic at 0. Also it is not continuous at 0, right? Because at 0 the function doesn't exist. So you see here how to prove it. Integral C 1 by z square dz, and C is here z mod is equal to 1. You put z is here e to the power I theta. So 0 less than theta less than 2 pi. What is here dz? dz is I e to the power I theta d theta. So this will be equal to, this integral I will be equal to here integral C. This is e to the power I theta whole square, e to the power I theta whole square, and it is here dz is I e to the power I theta d theta. It is 0 to 2 pi. So this is equal to, you have here 0 to 2 pi I e to the power I theta divided e to the power 2I theta, okay, d theta. So this is equal to integral 0 to 2 pi here I e to the power minus I theta d theta, okay, and if you integrate it, it is here 0, but the function is not analytic. That's why this inverse of the reverse of this Cauchy integral theorem doesn't work here, okay. So now the inverse is asserted if the function is continuous. Next, one more thing I have told, that the simply connected domain is also important, right? In view of that, let us consider one more example. So if you evaluate it, it will be here minus I by I e to the power minus I theta 0 to 2 pi, it is minus 1, it is e to the power minus 2 pi I, and it is minus here e to the power 0 is 1, right? It is here cos pi minus I sin 2 pi, here it is minus 1, 1 minus 1 is equal to 0. So therefore the converse of Cauchy's theorem is not true in general. To make the converse true, it is necessary that function is continuous, which is accompanied by the Morira's theorem. So now in another examples, I will show you that this multiple simply connected domain is also necessary, right? Necessity of simply connected domain. In view of that, let me to solve one example. Now you consider this example, right? Integral c dz by z, where c is the unit circle, lies in the domain in the annulus half less than z more less than 3 by 2. So suppose this is my center is 0 here, it is half, it is 3 by 2, right? This is here half, and this is 3 by 2, right? And what is my c here? My c here is unit circle z mod is equal to 1. So this is my c here, this is my c here, right? C is my z mod is equal to 1. So this is my 1. So you see the path here is the region here is this half less than z mod, the domain here is this annulus, right? And this domain is not simply connected, it is not simply connected, right? This domain is not simply connected, right? Even if the function is not analytic at 0, so 0 is outside, right? Here 0 is outside, right? And fz is analytic here, fz is analytic in D, right? As 0 is outside, but this integral c dz by z is not equal to 0. This integral is not equal to 0. To evaluate this integral, you see, already you know, if you put z is equal to e to the power I theta, dz is I e to the power I theta d theta, right? 0 less than theta less than 2 pi. So this integral I will be simply 0 to 2 pi here I e to the power I theta d theta by e to the power I theta, right? So here I theta, e to the power I theta cancelled. So this is equal to here I d theta, the integral is theta, right? This is from here 0 to 2 pi. So this is equal to 2 pi I. So actually this value of the integral is 2 pi I. The value of the integral is 2 pi I. But this is not 0. But if we apply Cauchy's integral formula theorem, then it should 0, right? So here Cauchy integral theorem doesn't work here. So here Cauchy integral theorem doesn't work. Why it doesn't work? As D is not simply connected. You can refer my previous lecture for simply connected. So simply connected domain means it should be free from any hole, right? It should free from simply connected domain means here free from any hole, right? And for the exact definition you should refer to my previous lecture, right? So this, even if this is the simpler version of this theorem, but this region, this domain is simply connected is necessary, right, to understand exactly what the Cauchy integral theorem is. Okay, now let us discuss some consequences of this theorem with few more further examples. Coming to one more example, evaluate this integral I is equal to this, where C is the circle and this circle. Now coming to solution I. So what is your fz in both the cases? Fz is 1 by z square minus 4, which is not analytic at z square minus 4 is equal to 0. So this implies z is equal to plus and minus 2, right? That is fz is analytic everywhere except at z is equal to plus and minus 2. So now let us see what is the path here. So the path here is, in I the path is a unit circle, center 0 and radius 1. So here is your 2 here, your 2 is here, and your minus 2 is here, right? So inside the path it is analytic everywhere. Inside the path, so that fz is analytic everywhere except at z is equal to plus minus 2, right, which is outside C, which is outside C. So that means fz is analytic everywhere inside and on C. So therefore, by Cauchy integral theorem, this integral C fz dz is equal to 0. Now likewise, coming to your example 2 here. In example 2, the center is at minus 5 pi, right? The center is at minus 5 pi. You see, the center is at minus 5 pi, right? This is my minus 5 pi. The center is at minus 5 pi, radius is 2. So the radius is 2. So it is something like that. So it will come to minus 7i. It will come to minus 3i. So but your 2 lies here. Your 2 lies here. Your minus 2 lies here. Right. So you see, it is analytic everywhere. Right. It is analytic everywhere, inside and on C. So therefore this integral here is 0. So this integral C fz dz is equal to 0, right, by Cauchy integral theorem. Okay. So accordingly you can evaluate your 2i. So we have to see that inside the path it should be analytic throughout. So coming to this integral, so this is your fz here, right? So your fz, it is a polynomial function. Fz is analytic everywhere. So here fz is analytic everywhere except at z is equal to minus 1, because at z is equal to minus 1 denominator 0, function is not analytic. So here what is the path here? So path is a circle with center at 0 and radius half. But this not analytic point is minus 1 is something here. So minus 1 is outside. So by Cauchy integral theorem, right, this integral is the integral C f dz is here 0. In that way it can be proved. Now let us see some further consequences of Cauchy integral theorem. Coming to another important result, if C be a closed contour, this entire this boundary of this rectangle is the contour C. So what is C here? C is C1 plus C2 plus C3 plus C4, right? And FZ is analytic everywhere inside and on C. FZ is analytic everywhere. Inside and on C, FZ is analytic, right? Inside and on FZ is analytic everywhere. Then your integral C FZ dz is 0, and which is same thing as integral over C1 plus integral over C2 plus integral over C3 plus integral over C4. So individually we can evaluate it by evaluating the line integral. We evaluate the individually by line integral, and this is by 0, and because this is by Cauchy integral theorem. So now this is 0, and if I individually evaluate them, this integral must be 0 here. Okay, so let us verify the Cauchy integral theorem for the integral C fz dz. So integral C zq dz, where C is a boundary of a rectangle, with vertices. So the rectangle is, the vertices are 1, -1, and it is -1 plus I, right? Now it is your 1 plus I, it is your 1 plus I, and it is your -1 plus I, -1 plus I. So this is the rectangle here, right? This is the rectangle here. So the rectangle, sorry, it is -1, this is -1, this is 1. So this is the rectangle. So this is the rectangle. Okay. So this is the closed contour here. This is the closed contour here, right? So this is my C1, this is my C1, this is C1, this is your C2, this is your C3, this is your C4. So here FZ is ZQ, and what is C? C is C1 plus C2 plus C3 plus C4, and ZQ is analytic everywhere in C, right? Inside and on C. So this integral, so therefore by Cauchy integral theorem, integral C ZQ dz is here 0. Now we have to verify this integral over C1. Now integral over C1 fz dz plus integral over C2 fz dz plus integral over C3 fz dz plus integral over C4 fz dz. So we have to find individually, and we have to check this is 0. So let us evaluate one by one. Now see, for C1, so this is your x-axis, means y is equal to 0. So your x is x here, right? And x varies from, this is your -1 0, this is your 1 0, this is your 1 1, and this is your -1 1. So x varies from -1 to 1. So x varies from -1 less than x less than 1. So what happens to your integral C? C1, this integral is integral -1 to 1. Okay, and here x is your ZQ, means xq dx, right? So what is your z here? Z is x plus iy, y is 0, so this is simply x here. So dz is equal to dx, or you may put x is equal to t, and accordingly your parametric representation, and accordingly you can also find it. Then coming to your C2, right? Coming to your integral C2. So over C2, you see here. So you see for C2, this line is parallel to y-axis at a distance 1. So x is equal to 1, right? X is equal to 1. So what is your z? Z is x plus iy. It is 1 plus iy. This is your z. So what is your dz? Dz is your I dy, and your y varies from 0 to 1. So 0 less than y less than 1. So you can write it integral 0 to 1 fz is 1 plus iy dy, right, I dy. So this is your f2. Then coming to your f3. So coming to your c3, in your c3 this line is parallel to x-axis at a distance 1 here. So this is your y is equal to 1 and x is varying from, this is x is from minus 1 to 1 in this direction, minus 1 less than x less than 1. So what is your z? Z is equal to x plus I into 1 iy. So what is your dx? Dx is here, dz is here dx, simply dx plus I0. So this integral will be integral here 1 to minus 1, 1 to minus 1. Here fz is zq, right? Just 1 second. So here likewise fz is here this q. So fz is zq. So what is your z? So x plus I whole q. And what is your dz? Dz is your dx. Now you see about this path C4. In C4 it is parallel to y axis at a distance minus 1. Okay, so it is x is equal to minus 1. And here z is equal to y is vary. X plus means here 1 plus y is varying iy, right? And the limit here is your y coordinate, it is minus 1, sorry, y coordinate is 1 and this y coordinate is 0. Here 0 less than y less than 1, right? Accordingly what is your dz? Here dz is I dy, right? So this integral here will be integral here 0 to 1, y coordinate here is, sorry, y coordinate here is 1 to 0, so it is 1 to 0. And here zq is 1 plus iy whole q and it is I dy. Sorry, it is here x is equal to minus 1 at a distance minus 1. So this is here equal to minus 1. So this is here minus 1. This is here z is minus 1 plus iy. Here z is equal to minus 1 plus iy. So it is here minus 1 plus iy. Minus 1 plus iy. Okay. Now if you evaluate this integral, this is equal to your 0. This is equal to your 0 and plus this will give you, if you simplify it, this will give you 1 by 4, 1 plus a whole to the power 4 minus 1 and here this will give you, and here this will give you 1 by 4, 1 minus I to the power 4 minus 1 plus I to the power 4. And if you evaluate it, this will give you 1 by 4, 1 minus I whole to the power 4. Now if you add them, if you finally add them, this plus this plus this plus this, it will give you your 0, which is giving you 0. So therefore it is verified. Okay, it is verified. So coming to one more important example, verify Cauchy integral theorem for the function fz is equal to z with the closed contour consisting of positive x-axis, positive y-axis and the parabola 8 minus 4x square. So what is your x-intercept? Putting x0, right? Putting x0. What is your y? Y is your 2 root 2 in positive first quadrant. If you put y equal to 0, right? If you put y is equal to 0, then x is 2. So here I am getting 2 0 and here I am getting 0 2 root 2, right? So this is my, this parabolic path here is, this point is here 2 0, this point is my 0 0 2 root 2, right? So this is the parabolic path and it's consisting of this positive x-axis, parabola along in the first quadrant and positive y-axis. So it is my path C1, it is my path C2, it is my path C3. So can I not evaluate this integral here? So here if I put x is equal to t, then my y will be here 8 minus. So now you see, so solving this, what is your 4x? 4x is this and x is 8 minus y square by 4. Now if I put y is equal to my t, then my x is 8 minus t square by 4. And what is the limit of y? Y varies from 0 to 2 root 2. 0 less than y less than 2 root 2. So 0 less than t less than 2 root 2. Okay. So accordingly, what is my parametric representation? My z2 for my C2 path. Here z2 is equal to here x plus iy. X is here 8 minus t square by 4 plus it, right, with 0 less than t less than 2 root 2. So accordingly, integral c, right, fz dz will be, what is your fz? Fz is your z. Fz is your z. So this is equal to integral 0 to 2 root 2. This is my z here. 8 minus t square by 4 plus it. This is my z. And what is my dz now? From this I can find dz. Derivative of this is minus 2t by 4. So minus t by 2 plus I dt. Right? It is here minus t by 2 plus I dt. Right? And accordingly you can evaluate it. Then here C1 and C2 you know. So integral C fz dz is integral over C1 plus integral over C2 plus integral over C3 f dz, and you can verify it. This is here. So actually this will give you minus 6. This will give you minus 6. And it will give you 2 minus 6 and it will give you 4. Okay. So this integral is 0. By Cauchy integral theorem, your fz is analytic everywhere. So this integral is 0. Right. By Cauchy integral theorem, this integral is 0. Fine. Now it is verified. So it is verified. Okay. Now coming to some important consequence of Cauchy integral theorem. Now Cauchy integral theorem for multiply connected region. It says like this: if C is a closed curve, right? If C is a closed curve and C1, C2, C3 are closed curve in C. Suppose we have another curve. Here is C1 is a curve here, C1 is a curve here, C2 is a curve here, C2 is a curve here, C3 is a curve here. Likewise. So if 3 curves, then it is triply connected, isn't it? If it is triply connected. It similarly n curves, then it is multiply connected, right? Then integral, this is my C, then integral over, then integral over, then your integral over cfz dz is same thing as integral over c1 plus integral over c2 plus integral over c3. Now this same theorem can be extended. Now this region is not only always, if I take this region like this, if I take this is my C, right? If I take this is my C and this is my C1 and this is my some C2 and this is my some C3, then also okay. Now it is analytic, right? It is analytic between this. It is analytic here between these curves, right? It is analytic between these curves. Then the integral is given like this, right? Now this, the consequence of this, we have here doubly connected region, right? We have the doubly connected region. So let C1 and C2 be two curves positively oriented such that C1 lies entirely within C2. Suppose this is my curve C2 and my curve C1. This is my curve C1. So C1 lies entirely within C2 and it is a doubly connected region. Fz is analytic here in the annulus as well as in the boundary also, right? As well as in the boundary also. So if C1 and C2 two curves positively oriented such that C2 lies entirely within C1, if Fz is analytic on the boundary C1 and C2 and the annular region, then integral over C1 fz is same thing as integral over C2 fz, right? Now principle of path deformation. Principle of path deformation or path independence. If fz is analytic in a simply connected domain, suppose fz is analytic in a simply connected domain, this, right, it is analytic throughout, it is analytic everywhere in a simply connected domain, then the integral fz is independent of path for any path. Suppose I am taking a 2 points here, this is a point B point, this is a point A point. Suppose a path, this is my C1 path. Suppose this is another path, suppose this path is my C2 path. Suppose I have my another path, this is suppose my C3 path, right? Then over any path the integral is same, right? Then you can say then the integral over A to B fz dz is same thing as integral over C1f is same thing as integral over C2 is same thing as integral over C3. Once the function is analytic everywhere in a simply connected domain, then the integral is independent of path. And here you see it is a doubly connected domain, okay, doubly connected. We are getting a hole here, we are getting 3 holes here, triply connected. Similarly multiply connected, I have a C4 here, right, I have a C4 here, so these are multiply connected, right? So these are the consequence of your Cauchy integral theorem. Now coming to the conclusion, okay, you see, once the integrand fz is analytic, right, within and on a simple closed path, then the integral c fz dz is 0. The path is closed. This notation I am using for closed, right? So you have to see this is analytic inside and on C, right? So this is very fundamental and easy consequences and easy applications once we verify the analyticity. Here the analyticity basically the polynomial functions and simple functions. So by the existence of the function you can understand the analyticity as we did. So you should follow some standard book, okay? So in my upcoming lecture I will discuss the Cauchy integral formula and Cauchy integral formula extension. I will discuss in the subsequent lectures. These are very important. Then now we should close this lecture here, right? If you feel this lecture is helpful and interesting, please like and subscribe to this channel, which will boost my motivation to upload subsequent lectures for your benefits. So thank you all. Have a nice day.